So in this lecture, we will look at queue operations and terminology, like some special operations on queue and some important terminologies we will look at. So if I talk about topics covered, like what are the topics we will be looking at? So we'll discuss basic structure of a queue. Then we'll look at some primary queue operations. Then we'll look into the concept of underflow and overflow with regards to queue. Then we'll look into some queue implementation rules. And finally, we will conclude this lecture with like by summarizing all the queue operations. So summary of all queue operations. So these are the topics we will be looking at in this particular lecture. So first, let us look into the basic structure of a queue. So you can consider any queue. Let us suppose a queue of people, like I have a group of people standing in a queue waiting for their turn. So any queue you take, it will have two things, front and rear. So this is the front of the queue, the starting point of the queue, and rear. That's the end of the queue, last of the queue. Now we already know that queue follows FIFO, the principle of FIFO. And what is FIFO? First in, first out. First in inserted will be the first one to be out. So definitely we can say that in the front, element will always be removed, because whenever I have to remove an element or an object from a queue, from where I will be removing? From the front. So from the front, elements are always removed. Elements are removed from the front. Similarly, if I talk about rear, new elements are added. New elements are always added at the rear. So this is the basic structure of the queue. So in any queue, you take two main positions will be there, the front and the rear, because these only will be the positions of interaction. If I want to interact with the queue, I can either interact at the front position or at the rear position. There is no other way I can interact. I cannot remove an element from the middle. I cannot add an element in the middle. So either I can remove an element from the front, or if I want to add a new element in the queue, I have to add it from the rear. So this is the basic structure of a queue. Now for more clear understanding, I'll take an array with 5 indexes, like index 0, 1, 2, 3, 4. Now let us suppose it contains some elements 10, 20, 30, 40, 50. So this basic array is representing a queue, and if it is representing a queue, it has to have a front and rear. So here the front will be 10, like front is index 0 and it is pointing to element 10. Similarly, rear is index 4 and it is pointing to element 50. Or to be more precise, you can call this array as Q. So if you are representing this array as Q, so you can write like this. Front will be Q of 0, which is 10, and rear will be Q of 4, which is 50. So this is the basic structure of a queue. So the idea is that any queue we take, like whenever I talk about a queue data structure, the structure will contain the front and the rear, because these are the only point of interaction. These are the points or the positions onto which we can interact in a queue. Now we'll look at some primary queue operations. So if I make a list of operations, so queue supports something called as NQ operation. NQ, you can also call it insert or push. Similarly, we have DQ operation. also called as delete or pop. We have front, or you can also call it peak. We have rear, size, is empty, is full. So these are like some special operations, queue operations. So all these operations one by one we will look at. So first let us look at NQ operation, which is also called as insert or push. Like these are like different names given to the operation. So as the names suggest, we can make out that NQ insert push means adding a element in a queue. So we already have a basic understanding that, let us suppose I already have a queue wherein some set of persons, they are like you take them as students waiting for their turn. So whenever you will add a new student, definitely you will add him at the rear, because we know that the terminology, we have the front and we have the rear. So it is very clear to us that NQ operation, what it means? It means adding a new element. NQ operation, what it will does is it will add a new element and at the rear, because whenever I will add a new element in the queue, I have to add it at the rear of the queue. So adding a new element at the rear of the queue, this is what will be done by the NQ operation. Now how it will be done, let us understand that. So let us suppose initially, like I am taking one example, I have empty queue. So initially I have empty queue, and in the queue there will be a front and the rear. So when the queue is empty, both front and rear, they will point to index -1, because empty queue, so index is -1. Now what I'll do is that I'll add a new element. So the operation will be NQ. So I'll perform the NQ operation and I'll add 10 to it. Now whenever the queue is empty, and in an empty queue if I'm adding any element, then both front and rear will get updated. They will get, its position will get incremented by 1. So both of them will become 0. It means the 10 will be inserted at position 0, because insertion in a queue will always be at the rear position. So wherever the rear is pointing, at that point the element will get added. So now rear is pointing to 0, and in this particular scenario both front and rear are pointing to 0. So that is where it got inserted. Now let us suppose one more NQ operation let us perform, and this time let us try to add 20. Now what will happen is that whenever we uh, perform the NQ operation, so 10 is already there in the queue. So front was pointing to 0 position, it will be 0 only. Only rear will get updated. So whenever we perform the NQ operation, rear will get incremented, the position, rear position. So initially it was 0, now it will become 1. So at that position, new element will get added. So 20 will get added at the index 1, because if you take it like array, so indexing starts from 0. So like this NQ operation works. Once again, let us do NQ 30. Like let's try to add a new element 30 to the queue. 20 is already there. Indexing will be something like this: 0, 1, 2, 3. Front position of the queue is 0. And since I am calling NQ operation, rear will get incremented. The position of rear, it will become 2. So at position 2, 30 will get inserted. So this is how NQ operation works. So we saw one very important point, some important notes. So whenever we perform the NQ operation, rear moves forward by 1. with each insertion. So with each insertion, rear will get updated. It will move forward by one. And one more very interesting point to be noted, if queue is full, then NQ will not be allowed, because it's understood that if the queue is full, no point of adding more elements to it because no space is there. So NQ is not allowed. So this was the NQ operation. Now we'll look at DQ operation. It is also called as delete or pop. So once again, you imagine a queue containing some students. Now, definitely, whenever you remove a student from the queue, the removal will be from the front. So we can say that what DQ operation will do, it will remove. It removes an element from the front of the queue. Let us visualize it with an example. Let us suppose I have a queue like this. It contains three elements 10, 20, 30. So if we talk about front and rear, so let me represent this queue as capital Q. So I can say that front is the position 0, Q of 0, that is 10. But to keep it simple, just in terms of position, I can say that front position is 0 and the rear position is 2. So this is the initial state of a queue. Now let us suppose I perform the DQ operation. So when I'll perform the DQ operation, rear will remain as it is because DQ will be done from the front and front will get incremented. So whatever was the previous front, the element from that there, it will get removed. So 10 will get removed. So only 20 and 30 will be there. 20 will become the front and 30 will be the rear. So this is how DQ operation works. So here we have vacant space. Once again, if I perform DQ, so rear will remain as it is, 2, front will get incremented, and whatever the previous front was pointing to, that element will get removed. So only 30 will be left and front will point to that position, and here both front and rear are pointing to that position, like 30. Now once again, if I perform the DQ operation, now in this particular scenario, 30 will get removed, like whatever the front is pointing to index 2. So the element from there, it will get removed and Q will become empty. And we know that whenever the Q will become empty, I have to make both front and rear as -1 because that's the indication that Q is empty. So in this particular scenario, both front and rear will become -1. So this is the DQ operation. Now we'll look at front or peak operation. So basically what it will do, it returns the element present at the front of the queue without removing it. So front operation, it returns the element at the front without removing it. For example, let us suppose I have a queue like this. Front is the position 0, index 0, and rear is pointing to index 2. If I will call the peak operation or the front operation, it will return the element at the front, that is 10, without removing it. So peak returns 10. And most important point, Q remains unchanged. Q remains unchanged. That's a very important point. So this is the front or the peak operation in the queue. Now we look at rear operation. So it is similar to the peak operation. It will return the rear of the queue without removing it, rear element. So this particular operation, rear operation, returns the element at the rear without removing it. So let us understand it with an example. So we have a queue like this. So the front will be 0, rear will be 2. The index of the front is 0, the index of the rear is 2. in this particular example. And if you call the rear function, it will return the element at the rear. So it returns 30. And very important point here also, q remains unchanged. So this is the rear operation. Now we look at size operation. So as the name suggests, this operation returns the number of elements currently in the queue. So the size operation returns the number of elements currently in the queue. So let us understand it with an example. So I have a queue. So the front index is 0, the rear index is 2. So if I call the size function, it will basically return the size. And what's the formula for that? Rear minus front plus 1. So this is the formula to calculate the size. So if we use this formula, so rear is 2 minus 0 plus 1. So it will return 3, which is the correct answer because the queue contains 3 elements. So this is the size operation. So the size operation of the queue will return the elements currently in the queue, and the formula for that is rear minus front plus 1. Now we look at is empty. Is empty, as the name suggests, this operation returns true if queue has no elements. So is empty operation, it will return true if the queue is empty, if the queue has no elements. Now one very important discussion we have to do, like there are some special conditions to check whether the queue is empty or not. So if front is minus 1, if front is minus 1, then definitely queue will be empty. Or if in circular queue, if the front becomes greater than the rear. So these are like two very important conditions which will indicate whether the queue is empty. So if front is minus 1, then queue is empty. If front is greater than rear, then also queue is empty. So this particular operation, queue operation, is empty. It will check for these conditions. And if any of these condition is satisfied, then it will return true. It means the queue is empty. The queue has no elements. Similar to this, we have an operation called is full. So definitely this function returns true if the queue is filled, if the queue is at its maximum capacity, if the queue is at maximum capacity. Now, very big question in front of us, how we will identify what are the conditions which will determine, like which will help us to determine if the queue is full or not. So for simple array queue, the condition is different, that we'll discuss. And for circular queue, the conditions are different, that also we'll discuss. So for simple array queue, the condition is if rear, which is the position, the index, if it reaches max size minus 1. Because in an array, definitely some size will be defined. We call it like the max size. So if rear reaches max size minus 1, it means we have reached the end of the array or the end of the queue. And it is an indicator that queue is full. For circular queue, modulo arithmetic will come into the picture, and this formula will alter a bit. So rear plus 1 mod max size, because rear plus 1 in circular queue will be the front, and we are doing it mod, we are doing it with the max size, so modulus arithmetic, because in circular index will keep on rotating. So if it becomes equal to the front, if it becomes equal to the front, it means we have the queue which has reached the maximum capacity. So let us visualize it with an example, especially the circular queue. Like we can look into both the queues like example. So simple array queue, let us look at some elements. So let us suppose I fill this queue fully. Now in this queue, rear is 3, max size is 4, because this array can contain only 4 elements. So 4 minus 1, 3. So rear is 3 and max size minus 1 is also 3. So this condition is satisfied. Like rear is equal to max size minus 1. Don't, yeah, this is an underscore. So max size minus 1. So we can see that this is the right formula or the right condition to determine whether the queue has reached its maximum capacity. And for circular queue, let us visualize it. So I have a circular queue, something like this. And definitely looking at this, I can say that this queue is filled, like it is full, it is full. It is at its maximum capacity. Now, definitely this is the front, this is the rear. And max size means 1, 2, 3, 4, 5. Total 5 elements it can hold. So rear plus 1. So in our scenario, it will be 5. Like rear is 4. So 4 plus 1 modulo max size. Max size is 5. So 5 modulo 5. So remainder will be 0. So it is 0. And what is front? Front is 0. So since this condition is satisfied, LHS is equal to RHS. Because here, in this particular scenario, rear plus 1 modulus max size, if you do, you will get 0. And front is also 0. So mathematically, we can say that the queue is full, circular queue is full. And looking at the circular queue also, it is very clearly, we can understand that it is full. So the conditions for the is full is important. For circular queue, it is rear plus 1 modulus max size if it is equal to front, the front index, then the circular queue is full. And for simple array queue, the condition is rear equals to max size minus 1. So this is the is full operation. So we covered all the operations of the queue. Now we look at underflow and overflow conditions. So first let's focus on overflow condition. Now what exactly is overflow condition, or when this condition will occur? So overflow condition occurs when we try to enqueue when the queue is already full, or when the queue is already full. So overflow condition occurs when we try to enqueue when the queue is already full. Like just imagine the queue is already full and we are trying to add more elements to it. Then overflow will occur. So very easily we can visualize it with an example. Like I have a queue which is already full, and in this queue, front is 0, rear is 3. And definitely, see now no overflow condition has occurred. In this particular scenario, the queue is very stable. But if you perform this operation, NQ 50, what will happen? Uh, Rear will become 4. So at this particular point, when you do NQ 50, what exactly will happen is rear will become equal to max size. And whenever rear will become equal to max size, it will lead to overflow condition. So this is the idea of overflow. Similarly, we have underflow condition. So underflow condition occurs when we try to dequeue when the queue is already empty. So when we try to dequeue when the queue is empty, underflow condition will occur because queue is already empty. And if we try to dequeue an empty queue, then it will be underflow. So let's visualize it with an example. So in this particular queue, we can see it's empty. So empty queue, we know that both front and rear will be minus 1. So if we try to do dequeue operation, condition is if front is equal to rear is equal to minus 1, or front is greater than rear. It means queue is empty. And if you are performing an operation, DQ operation, when the queue is already empty, it will lead to underflow condition. So this is the overflow and underflow condition in queue. Now we look at some queue implementation rules. So first let's discuss indices. And we know that in the queue, only 2 points of interactions we have, front and rear. So the indices of interest will be the front and rear pointers. And whatever discussion we are making, we are focusing on simple linear queue. So for linear queue, we have already seen front pointer is basically position of first element. Rear is the position of last element of the queue. So this is already clear to us. Now one very important point, both indices like both front and rear, both move forward only. This is very interesting observation. Like both front and rear indices, no matter what you perform NQ operation or you perform DQ operation, front and rear they will move in the forward direction only. They cannot move in the reverse direction. So both move forward only in linear queue. Now in linear queue, one very big drawback is there, like the issue of unused spaces in the beginning of the queue after many DQs. So linear queue, it causes unused spaces in the beginning after many DQs. So this is a problem with the linear queue. Like we can visualize it. So suppose this is the queue. So when I perform the DQ operation, first element will be removed. Then once again DQ, second like this will be removed. Then so you can see that in the linear queue, we have unused spaces in the beginning, because these two spaces are now, why it is unused, because when you insert an element you have to insert from the end in the linear queue. So these elements are unused like that. So that's a drawback of a linear queue, and circular queue fixes that problem. But like in terms of indices, we got some very interesting observation that both front and rear pointers they move in the forward direction only. Now we'll focus at movement of pointers. So when we perform the NQ operation, we know that insertion will always from the end, from the rear in the queue. So rear will get incremented. Rear will get incremented, and in that position, the updated position, new element will get added. So value is the element which we are trying to insert. So this is how the movement of pointers will be for the NQ operation. Rear will get incremented by 1, and in that queue at that new position value will get inserted. For DQ, we know that DQ will always be done from the at the beginning. So front pointer will get incremented. So what will happen is that first whatever is the current front value will get it and store it in a variable. So whatever is the current front value will get it and then increment the front pointer. So this is how the movement of pointers will be for the DQ operation. And one very important condition, when Q is empty, then both front and rear will be -1. So both front and rear will be -1. If front and rear are -1, means Q is empty. So this is the movement of pointers. Now we look at some constraints and limitations. So first we look at linear queue problem. So we already saw this. So linear queue, what's the problem was? Unused spaces. Because in linear queue, DQ operation, when we do, elements will get from the beginning, and after subsequent DQ operations, there will be a scenario wherein there will be many unused spaces in the beginning of the array or of the queue, beginning of the queue, and those spaces will be unused because when you insert new element, you will insert it at the end. Like I have this queue. When I perform the DQ operation, 10 will get removed. Now this space is unused. Let us suppose 30, like the queue is looking something like this, for example. Now you know that whenever you will insert a new element, insertion will occur always at the rear. So new element will get added here. So this space will be never utilized. Similarly, one more DQ operation you will perform, element at the front will get removed. So this space is also unused because when you insert a new element, that will be at the rear. So these spaces will become unused. So that's the problem of linear queue that we already saw. Now, circular queue can fix this problem. So we saw the limitations of the linear queue, and circular queue can fix it. So we'll look at the circular queue fix. Now in circular queue, a modulo arithmetic is applied, and both rear and front, they follow the formula. Like for rear it is rear plus 1 modulo max size. So what will happen is that whenever you increment the rear, because in linear we just increment, but now we increment the rear also and we divide it with the max size. And because of that, what will happen, I'll tell you. And in front also, the same concept. Will increment the front and divide it with the max size. Like it is the modulus, not division, it's modulus. It's the modulo operation. So modulo. So modulo operation, I think you know, uh, it will give the remainder. Now let us visualize it with an example. So let us suppose I have a circular queue like this and it has two elements. Now front is this index 0 and rear is this index 1. Now let us suppose you have to perform NQ operation. So when you perform the NQ operation, we know that rear will get updated because we will add at the end. So here max size is 1, 2, 3, 4, 5, 6. Here max size is 6. So rear will become whatever is the current value of rear plus 1. So 2. So 2 modulo 6. It will be 2 because so now the rear will become 2. So rear will become 2. So rear will be here and new element will get added at this point, at this position, at this index. Now let us suppose you performed a DQ operation and we know that in a queue element gets removed from the beginning. So front will get updated. So front plus 1 modulus max size. So front is 0. So 0 plus 1, 1. 1 modulo 6 will be 1 itself. So front will become 1 and this element is removed. Now front is pointing to this. Now earlier what used to happen was this used to be an unused space because in linear queue like this is unused because it is inaccessible. But in circular queue, the beauty of this approach or is that let us suppose now you are doing subsequent n queues. So with every n queue, rear will just get update by 1. Let us suppose you are here. So now rear is pointing to this. Rear is pointing to this 5. Now one more NQ if you want to do, then what it will be, rear will get incremented. It will become 5 plus 1, 6. 6 modulo 6. Remainder will be 0. So now rear will point to 0 index. And whatever new element you will insert, that will get inserted at this point, at this index, at this position. So this is the idea. So in circular queue, the idea is very clear that unused spaces, we are able to access it. We are able to make use of it. And it is a very powerful technique, because just imagine if you have millions of records, or buffer, like because queue you use it in like buffer, so 1 megabyte, 1 MB buffer, or 5 MB buffer, for example. And linear queue, definitely it will be less efficient, because a lot of unused spaces you might have. But circular queue is fixing that problem, as we just now saw it. Now, one more very interesting limitation or constraint of a queue is no random access. No random access. And it is making sense also, because in queue we already saw that the point of interaction is only the front and the rear. Whatever element you have to add or remove, you can do it from the front or rear only. We cannot insert in the middle, or we cannot remove a element from the middle. So no random access is allowed, and it's a constraint of a queue. So this is how the queue is designed. So queue inherently comes with this constraint, or with this limitation of no random access. So we looked into some queue implementation rules. Now we'll look at summary of all queue operations. Now see, basically we looked at different queue operations like NQ, DQ. We know the meaning of it. NQ means add element at the rear. DQ means remove element from the beginning. Front or peak will return the front element without removing it. Rear operation will return the rear element without removing it. Size will return the size of the queue, that is rear minus front plus 1. Is empty will check whether the queue is empty. Is full will check whether the queue is full. Now, very interesting observation. For all these operations, if we look at the time complexity, it is big O of 1. Big O 1. Big O 1 means constant time operation. We can feel it. Constant time operation. Constant time operation means independent of the size. Very, very powerful point. Independent of the input size. Independent of input size. Because see, we saw all the operations. In that, we saw that we are just incrementing. Like when you are doing the NQ operation, you are incrementing the rear by 1. No loop was involved. No iterations were involved. So all these operations, they involve just either incrementing the rear or incrementing the front, or returning the front or the rear value. That's it. Or some basic comparisons. And all those operations are of big O 1, constant time operation. So that's a very interesting thing about the queue. Let us suppose you have queue of millions of records. Now you want to add a new record to it. You can do it in a constant time, because you don't need to touch previous records. Just rear you have to update. That's it. And if you want to remove a record, that's also big O of 1, constant time operation. Don't want to, you don't have to touch anything in middle. So because of this constant time operation, queue has got lots of applications. They are ideal for real time operations, because in real time operations, speed is very important, like real time systems. So when you design real time systems, in operating systems also we make use of the queue. So in real time systems, queue has got very good applications in buffering, because speed matters a lot in buffering, or in scheduling. Wherever there is a scope of first come first serve. In buffering, there is a scope of first come first serve. In scheduling, there is a scope of first come first serve. So the scope of first come first serve along with constant time operation makes queue an ideal data structure for real-time systems, buffering and scheduling. So friends, finally we completed the lecture, that is the queue operations and terminology. I hope you liked it. You got some good understanding. So do subscribe to this YouTube channel. Do like this lecture, share it in your circle. So thanks for watching. Thanks for your time.